The whispers of ancient ice. Imagine it for a moment. You are standing on a world where the entire horizon is ice. There are no blue seas, no green forests, not even a clear sky, just a diffuse light, as if the sun were trapped behind a frozen pane of glass. The air is so cold that every breath seems to steal a piece of life from you. And yet, in that impossible world, Earth was more alive than ever. Throughout its history, our planet has gone through transformations so drastic that they defy imagination. And among them, the ice ages are like crumpled pages of a book we have almost forgotten to read. We think of glaciers, mammoths, and white landscapes, but that is only the surface. Beneath that mantle of ice and silence, hide secrets that could change what you think you know about the history of life and about the history of ourselves, because these ages were not simply prolonged winters, they were authentic planetary restarts. Some left scars that can still be read in the mountains and oceans. Others perhaps erased entire chapters of civilizations, of which nothing remains but an echo in the stone. And perhaps some are yet to be discovered. In this journey, we are going to go back millions of years beyond what the history books tell. We are going to walk through frozen deserts that were once tropical seas, to look at fossils that seem out of place, to listen to the murmur of ancient ice that still guards the memory of disappeared worlds. And if these kinds of slow, profound questions are also your kind of questions, stay with me. On Dato Terra, curiosity finds its place, and science takes its time. You can subscribe and accompany me on every exploration, because what we are going to discover together is as vast as time itself. The ice holds its secrets. Let us go look for them. Imagine a rock, cold to the touch, grey, seemingly mute. You hold it in your hand, and it seems to say nothing. But that rock can be older than any forest, older than any modern ocean, even older than the mountain ranges we know today. Inside it, stored like layers of an immense book, are the footprints of a time when the entire Earth was submerged in a white silence. A time that for a long, long time we thought we knew, until we discovered that it was not so. The official history of the ice ages that we learn in school usually begins and ends with a few great glaciations. The most recent one, which shaped the ice landscapes at the poles and gave rise to legends of mammoths and prehistoric hunters. But the truth is that these are barely the last pages of a much longer story. A story that stretches over billions of years and hides episodes so extreme that even today it is difficult for us to understand how life could have survived them. Geologists call these episodes glaciations, but that term barely does them justice. It was not just about intense cold. Some of these glaciations were so profound that they covered entire continents with kilometers of ice. Others, on the other hand, were more subtle, small ambushes of cold that changed the course of rivers, seas, and migrations. And between one and the other, the Earth experienced periods of heat, violent thaws, and seas that rose and fell as if breathing. Ice is a patient narrator. It does not shout its stories. It whispers them. And to hear it, we need tools, science, and time. Sedimentary rocks, for example, can contain tiny crystals that only form under conditions of extreme freezing. By analyzing them, scientists can go back millions of years into the planet's memory. In some cases, they have found evidence of ice in latitudes where the climate is tropical today. And here the first question that shakes us arises. How many ice ages have existed that we have not even registered yet? What we know is based on incomplete clues, rock fragments, isotopes in ice cores, and chemical traces in ancient seabeds. Every new discovery is like finding a lost word on a torn page. and sometimes those words contradict everything we thought we knew. For example, for decades, it was thought that the first great documented glaciation occurred about 2.3 billion years ago in what is known as the Huronian glaciation. A practically mythical role was attributed to it, the moment when the atmosphere began to fill with oxygen, a change that altered the climate and caused vast regions to freeze. But more recent findings suggest that there may have been glacial episodes even before that. If true, we would be talking about a young planet that already knew the cold, even before there was enough oxygen to fuel life as we understand it. Imagine it, an Earth without trees, without animals, without even flowers, only oceans, rocks, and primitive bacteria, and suddenly, a cold so deep that the sea began to freeze from the surface down. In that world, life had to find refuge in underwater crevices, near volcanic fumaroles, in tiny pockets of liquid water trapped under the ice. But the most intriguing thing is not just that these glaciations occurred, but that they left traces that do not fit with our understanding of geology. In some places, glacial deposits appear right below layers of rock formed in warm waters. It is as if, in a matter of thousands of years, the planet had gone from tropical heat to eternal winter. This rapidity is disconcerting because it suggests that something, or someone, if we allow ourselves a speculative moment, could cause abrupt climatic changes. We are not talking about conspiracies, but about genuine geological mysteries. For example, a sudden change in Earth's orbit, an asteroid impact that raised dust and blocked sunlight, or massive volcanic eruptions capable of filling the atmosphere with aerosols. Any of these events could have led to an ice age in a matter of decades or centuries, a sigh in geological terms. Geology speaks to us with the language of patience, but paleontology adds a more unsettling nuance. Life seems not only to survive these cataclysms, but sometimes to thrive after them. After the great glaciations, the diversity of organisms often increases, as if the ice acted as a sieve, eliminating the fragile and leaving room for the new to emerge. It is a pattern so repeated that some scientists call it the ice paradox. Extreme cold, far from killing life, can prepare the ground for its expansion. This is where the whispers of the ice become almost philosophical. If life on Earth has gone through so many restarts, how many times has it had to start from zero? How many stories have been erased before we could write them? And this question leads us to an even bolder one. Could there have existed complex life forms, perhaps not human, but intelligent, in remote epochs that disappeared, without leaving more trace than some strange fossils and ruins that today we confuse with natural formations? We know that the footprints of time are cruel. The ice erodes, glaciers drag and destroy. If something existed before the last dozen known ice ages, its remains could be pulverized, buried under kilometers of sediments, or submerged in seas that today seem eternal. Glaciers, in their apparent immobility, are great travelers. Over millennia they move, advance, retreat, carrying rocks, sand, and fragments of history with them. Sometimes, in their thaws, they release bodies of animals that were trapped tens of thousands of years ago, perfectly preserved, with skin, hair, and even food in their stomachs. If that can happen with a mammoth, what could be hidden even further back in time? Ancient ice does not speak loudly. It does not issue warnings or reveal secrets easily. It just keeps. It waits. And we as a species are barely learning to read it. Modern techniques of isotopic analysis, the drilling of ice cores in Greenland and Antarctica, and even the study of caves and stalagmites allow us to reconstruct past climates with increasing precision. But we are still far from completing the map. Think about this. If we could go back to the moment just before one of these forgotten ice ages, perhaps we would see a planet in precarious balance, a balance that could be broken by a minimal change in the amount of sunlight, in the composition of the air, or in the ocean currents. And once broken, the ice would advance with relentless slowness, covering everything in its path. The first chapter of this journey is not so much a history lesson as an invitation to listen, because the whispers of ancient ice not only speak to us of the past, they also warn us about the future. The cycles that led the planet to freeze have not disappeared. They are still there, waiting for the right conditions. As we advance in this exploration, remember that what we think we know about the climate, life, and history of the Earth may be just a fragment. The ice is patient. We are not so much. And perhaps it is that difference that determines whether in a distant future, someone will speak of us as a civilization lost under the snow. More than 2 billion years ago, the Earth was an unrecognizable place for us. The sun shone less than today, the days were shorter, and life was reduced to simple forms. Colonies of bacteria, cyanobacteria, that painted some shallow seas, blue-green, and microorganisms that were barely beginning to experiment with complexity. There were no trees, no flowers, no animals. And yet, it was in that primitive world where something occurred that almost ended everything, the first eternal winter that we know of. This episode has been given an imposing name, the Huronian glaciation. According to geological evidence, it lasted for hundreds of millions of years. By our standards, it is inconceivable. We measure time in decades, or, with luck, in centuries. But the Huronian lasted so long that had humans existed then, they would have lived and died generation after generation without ever seeing a thaw. Geologists have found unequivocal traces of this period in ancient rock deposits in what is today Canada, South Africa, and even parts of India. These are tillites, rocks formed from sediments dragged and compressed by glaciers. In these layers, the pattern is clear. First ice, then a layer indicating a brief thaw, and then ice again. An alternation that repeats itself, but always under the dominance of the cold. But what could have caused such a global freezing? The most accepted answer involves one of the deepest changes in Earth's history, the Great Oxidation Event. Before this event, the atmosphere was practically free of oxygen. Cyanobacteria began to produce it as a byproduct of photosynthesis, slowly releasing it into the air. What is essential for us was a poison for many life forms of the time. Millions of anaerobic organisms died, drastically altering the planet's biological composition. But oxygen had another unexpected effect. It reacted with the methane in the atmosphere, a greenhouse gas much more potent than carbon dioxide. Methane became carbon dioxide and water, reducing the planet's ability to retain heat. The result was an abrupt drop in global temperature, enough for the seas to begin to freeze and not stop. Imagine that moment. In the tropics, where the sunlight hit hardest, the temperature dropped enough for sea ice to form and persist. As the white ice covered more surface, it reflected more and more sunlight back into space, cooling the planet even further in an implacable, vicious cycle. The Earth slowly became a cosmic snowball. Despite how dramatic it sounds, the planet was not completely dead. Under the ice, in the depths of the oceans, hydrothermal vents maintained oases of heat and nutrients. There, in the darkness, entire communities of organisms continued to thrive, oblivious to the eternal winter. It is likely that in those same conditions, some genetic adaptations arose that would later allow life to expand again when the ice retreated. The Huronian also leaves us with an intriguing message. Life is not only resilient, but adaptable to extremes that are difficult for us to imagine. The microorganisms that survived were not the biggest or the strongest, but those that found creative ways to withstand the scarcity of light and heat. Some may have entered states of extreme latency. Others clung to niches where geothermal heat kept the water liquid. But if this winter lasted hundreds of millions of years, how did it end? The most accepted theory is that volcanic activity was the key. Although the planet was covered in ice, volcanism did not stop. Volcanoes continued to release carbon dioxide, and since the ice blocked much of the processes that normally removed it from the atmosphere, such as erosion and absorption by non-existent land plants, this gas slowly accumulated. Over millions of years, the concentration increased enough to reverse the cooling. The greenhouse effect warmed the planet again, melting the ice and returning the liquid seas to their open state. This change must have been as drastic as the original cooling. Imagine glaciers that had been immobile for eons, suddenly beginning to fracture and release gigantic rivers of icy water into the oceans. The ocean currents, asleep under the ice, would have awakened violently. Water levels would have risen extraordinarily, flooding regions that had never seen the sea before. It is tempting to think of this episode as a disaster, and it was for many life forms, but it was also a rebirth. At the end of the Huronian glaciation, the planet was unrecognizable. New habitats had formed, the atmosphere had stable levels of oxygen, and the life that had survived was ready to diversify. It was, in a way, a deep cleaning of the biological board that set the stage for future evolutionary leaps. Here, however, a fascinating question arises. Some geologists suggest that there may have been several glacial events prior to the Huronian, but that the evidence was erased by subsequent geological processes. The Earth is a living planet in constant change. Tectonic plates recycle the crust, volcanoes bury ancient strata under fresh lava, and erosion slowly erases the traces. If older glaciations existed, they could be buried so deeply that we may never find them. This thought forces us to accept an uncomfortable reality. The geological record is incomplete, and always will be. What we know is barely a fraction of what really happened. And in that fraction, the Huronian is the first great window into a planet that could have frozen and thawed several times before reaching us. Beyond its geological history, the first eternal winter poses a philosophical question. If life could withstand hundreds of millions of years of extreme cold, what else is it capable of? And if that is true for Earth, what implications does it have for the search for life on other planets or icy moons like Europa or Enceladus? Perhaps the ice is not an obstacle, but a sanctuary. The Huronian is not just an ancient chapter. It is a reminder that Earth's climate can change beyond any scale that we can control or predict, and that in those changes, what survives is not the strongest, but the most flexible. Think of the entire planet as a white, bright sphere, suspended in the darkness of space. It is not a poetic exaggeration. There was a moment in Earth's history when practically its entire ocean was covered by ice, from the poles to the equator. There were no blue seas, no green coasts, no grey clouds floating over open waters. Only a solid, shimmering mantle that reflected sunlight like a cosmic mirror. This scenario is known as the snowball Earth hypothesis, and according to geological evidence, it did not happen just once, but several times, between 700 million and 500 million years ago. It was an unsettling and fascinating period, called the Neoproterozoic, in which the planet experienced some of the most extreme glaciations in its history. The evidence is in the rocks. Glacial sediments, found in latitudes that are tropical today. Layers of material deposited by glaciers immediately covered by chemical formations, typical of warm waters, and a repeated pattern of global coolings followed by sudden thaws. This data has led many scientists to accept that, indeed, the Earth may have been frozen almost completely. But how could an entire planet fall into such a state? The most accepted explanation combines several factors: a decrease in solar radiation, changes in Earth's orbit, and the arrangement of the continents that favored the formation of ice. During the Neoproterozoic, most of the continental masses were grouped near the equator. This might seem contradictory, because we would think that the equator is the warmest zone. However, this arrangement affected ocean and atmospheric currents, allowing ice formed at high altitudes to spread rapidly towards low latitudes. As the ice expanded, the planet's albedo, its ability to reflect sunlight, increased, sending more energy back into space and cooling the surface even further. The cooling became self-sustaining, a vicious cycle from which it was almost impossible to escape. Under that frozen dome, life had to face an unprecedented challenge. The oceans were not completely solid. Under the ice, in deep areas, the water remained liquid thanks to the planet's internal heat. There, near hydrothermal fumaroles and sources of chemical nutrients, communities of microorganisms survived. Some of these bacteria and microscopic algae perhaps found refuge in isolated lagoons or in pockets of liquid water under glaciers, keeping alive the spark that would later allow the rebirth of the biosphere. The most extraordinary thing is that the snowball Earth was not a brief parenthesis. The records suggest that it could have lasted tens of millions of years. If for a human being, a single decade of winter would be unbearable, imagine entire generations of organisms adapting to a world without warm seasons, where the sky looked pale and the sunlight barely penetrated the ice. And yet, this stage was not just a dark chapter. It was also an evolutionary laboratory. The extreme cold, the scarcity of light, and the geographical isolation forced life to develop new strategies. Resistance to freezing, metabolism based on chemical compounds, and perhaps the first forms of cooperation between organisms. When the ice finally retreated, the surviving species had unprecedented biological tools to expand and diversify. But how did an entire planet covered in ice melt? The key seems to be once again in volcanic activity. Even in the midst of a global winter, volcanoes continued to release carbon dioxide into the atmosphere. Without rain or rivers to dissolve it and drag it into the ocean, the gas accumulated over millions of years. A point was reached where its concentration was so high that the greenhouse effect overcame the ice's albedo. Then, slowly at first, and then accelerating, the planet began to warm. The thaw was in all probability violent. Imagine glaciers that had remained immobile for millions of years, cracking and collapsing in enormous blocks towards newly released seas. The oceans, deprived of circulation for so long, would have reactivated, releasing trapped nutrients that fueled massive explosions of phytoplankton. This biological rebirth may have been one of the triggers for what would be the Cambrian explosion a few million years later, the moment when complex life diversified unprecedentedly. However, not everyone accepts the idea of a completely ice-covered Earth. Some scientists propose a more moderate version, the slushball Earth, in which ice covered much of the planet but left equatorial areas of open sea. This would have allowed photosynthetic life to continue, without the need to take refuge only in deep waters. Whatever the correct version, the fact is that the Neoproterozoic climate was radically different from the current one and had consequences that still resonate in our evolutionary history. What is most fascinating about the snowball Earth is the paradox it holds. An apparently dead planet that at the end of its freezing emerged more alive than ever. It is as if the ice had acted as a necessary pause, a kind of global restart that allowed the biosphere to reinvent itself. This idea inevitably leads us to a broader reflection. If life could not only survive but thrive after a planetary freeze, what does that tell us about the possibility of finding life on other icy worlds? Moons like Europa or Enceladus, covered by thick layers of ice, could be, in this sense, echoes of our own history. Perhaps under their ice, an evolution is brewing that one day will flourish with the same intensity as it did here. And yet, there is an unsettling nuance in all of this. The Earth's cycles of ice and thaw are not just past phenomena. They are part of the very nature of the planet. The orbit, the inclination of the axis, the arrangement of the continents. All these factors can align on scales of millions of years to take us back to extreme scenarios. The fact that today we live in an interglacial period with relatively stable and temperate climates is a fortunate circumstance, but not necessarily permanent. The snowball Earth reminds us that the climate is not a constant, but a cosmic choreography in which cold and heat follow each other as inevitable acts of the same work, and that for life, each act brings with it not only challenges, but opportunities for transformation. At this point in our history, the planet had demonstrated two things: that it could freeze to the limit of the imaginable, and that it could return from that limit with renewed force. What comes next in our journey is to discover how, in the midst of that sway of ice and fire, impossible landscapes emerged, where glaciations and volcanism coexisted to shape a world as beautiful as it was hostile. Imagine a horizon divided into two worlds. On one side, the ice advances like a silent wall, fracturing into deep crevices that seem endless. On the other, a volcano throws columns of smoke and fire into the sky, staining the snow with orange and black tones. The roar of the earth and the icy silence coexist in the same scenario. This is not a fragment of science fiction. It is a faithful portrait of the Earth at various moments in its history, when absolute cold and the most intense heat faced each other head-on. The ice ages were not periods of total stillness. Although enormous glacial layers covered entire continents, the interior of the planet remained alive. Plate tectonics did not stop. Volcanoes did not stop spitting magma, and internal forces continued to remodel the crust. This clash of extremes created unique landscapes where glaciers and lava coexisted, leaving traces that we can still find today in ancient rocks. During the most severe glaciations, including those of the Neoproterozoic and the last great glaciation of the Pleistocene, volcanoes became islands of heat in the midst of frozen oceans. In places where the Earth's crust was thinner or tectonic activity more intense, magma found an outlet, melting the surrounding ice and forming temporary lakes that later froze again. These spaces could become oases for life. In some cases, the contrast was brutal. Imagine it. Kilometers of ice extended as far as the eye could see, and in the middle, an open fissure released incandescent lava that ran through ice tunnels, instantly evaporating the water and generating columns of steam that rose towards a grey sky. The thermal shock caused sudden explosions, fragmenting the ice into blocks that fell like collapsed walls. The ice, although cold and apparently immobile, also exerted pressure on the crust. In regions where the layers reached several kilometers thick, the weight could deform the bedrock, generating tectonic instability. This, in turn, could increase the frequency of volcanic eruptions in glacial areas. Thus, the ice not only coexisted with fire, it sometimes caused it. One of the most fascinating examples of this interaction is found in Iceland, a place where glaciers and volcanoes have coexisted for millennia. There, subglacial eruptions have produced phenomena called jökulhlaups, sudden floods caused by the massive melting of ice due to volcanic heat. Although today these events are relatively small compared to those of the past, they give us an idea of what could have occurred on a much larger scale during the ancient great glaciations. But the story of ice and fire is not just a visual spectacle. It also played a fundamental role in the evolution of the atmosphere and climate. During periods of extreme glaciation, volcanoes released enormous amounts of carbon dioxide and other gases. Since the planet's surface was covered by ice, the absorption of these gases was minimal. This allowed them to accumulate in the atmosphere generating a progressive greenhouse effect that could eventually contribute to ending the Ice Age. At the biological level, these extreme encounters created microenvironments where life could adapt and diversify. Around the subglacial volcanic areas, the heat and nutrients dissolved in the water formed isolated ecosystems. Here, extremophile bacteria and archaea thrived in conditions that would have been lethal for most organisms. It is possible that these thermal refuges were key to the survival of life during the hardest periods of planetary freezing. In the geological record, these battles between ice and fire are engraved in rock layers that seem contradictory. Glacial deposits covered by lava flows, or volcanic ashes trapped under strata of fossil ice. Each of these traces is a testimony to the resilience of the planet and the life that inhabits it. The impact of this interaction was not limited to the primitive Earth. Throughout the ages, even in more recent glaciations like the Pleistocene, volcanism played an important role in the transition to warmer climates. About 70,000 years ago, for example, the eruption of the Toba supervolcano in what is today Indonesia released so much material into the atmosphere that it altered the global climate for years. Although this event coincided with a cold phase, its immediate effects included cooling due to the ash and, in the long term, an increase in greenhouse gases. The fire also changed the glacial landscape in ways that we can still observe. In areas like the Volcanoes National Park in Alaska, eruptions have left tunnels and caverns in the ice, some of which remain stable for decades. These formations could have served as corridors for certain species to move, or for seeds and spores to find temporary refuge. But beyond the scientific, the image of ice and fire together awakens something deeper in us. It is the physical representation of two opposing yet complementary forces, one that conserves and stops, and one that destroys and transforms, both necessary to shape a living planet. In the narrative of the Earth, these episodes were moments of tension and change, points where stability broke to give way to something new. The ice, with its relentless cold, seemed invincible until the fire, with its unleashed fury, opened crevices and paths, and the fire, with its uncontrolled heat, found its limit in the white vastness that surrounded it. If we look further, even towards other worlds, this duality is not exclusive to our planet. On icy moons, such as Enceladus, internal heat creates geysers that cross layers of ice tens of kilometers thick, throwing steam and particles into space. On Jupiter's moon Io, although there is no ice, extreme volcanism reminds us that internal fire is a constant in active planetary bodies. The interaction between internal heat and a frozen surface could be a clue to understanding not only our past, but also the possible landscapes and climates of distant worlds. The truth is that after every encounter of ice and fire in the history of the Earth, something changed. Sometimes it was the end of a glaciation, other times the creation of a new ecosystem, and always an enduring trace in the geology, like a whisper that the extremes not only oppose each other, they also need each other. In our journey, this chapter marks a transition. From the absolute dominion of the ice, we move to a planet where fire begins to reclaim space, where internal forces make themselves felt and open the way for even deeper transformations. Because after the clash of these two titans, what follows is a story that mixes geology, biology, and a touch of human mystery. The impact of the ice ages on the first cultures and on civilizations that only perhaps existed before we believe. When we think of the ice ages, the first thing that comes to mind are pristine and hostile landscapes, endless glaciers, wind-swept tundras, and herds of mammoths moving in the snow. It is easy to imagine a world empty of cities, temples, or roads. And yet, throughout history, unsettling questions have arisen. What if not all the footprints of humanity, or something similar, began in the current warm period, and ancient glaciations erased entire chapters of civilizations that existed before our official history began? In archaeology, the absence of evidence does not always mean the absence of presence. What we know today as civilization, agriculture, writing, cities, dates back to a few thousand years. But the Earth has millions of years of history, and glaciations are authentic erasers of footprints. A glacier not only covers the terrain, it crushes it, drags it, and grinds it. Under its weight, constructions crumble, stones erode until they become unrecognizable, and any organic material disappears. What remains may seem millennia later, like a natural formation. The last glaciation, which began about 115,000 years ago and ended about 11,700, covered much of North America, Europe, and Northern Asia under kilometers of ice. If an advanced civilization had existed in those territories before that moment, its remains would have been buried, fragmented, or dragged to the sea. The layers of sediment deposited after the thaw would be like a veil over any physical evidence. And here, a fascinating element comes into play: the stories and myths of cultures around the world that speak of earlier times, of submerged cities or cities destroyed by a great cold. The Inuit of Greenland, for example, preserve oral accounts of fertile lands that suddenly froze. In South America, some Quechua and Aymara traditions speak of the Great Freeze that ended entire peoples. Although we cannot take these legends as direct evidence, we can consider them as echoes of memories transmitted through generations. Outside the glaciers, the sea is another great guardian of secrets. During the ice ages, much of the planet's water was trapped in the form of ice, which made the sea level up to 120 meters lower than it is today. This means that enormous extensions of land that are under the ocean today were then habitable plains. It is in those submerged areas where remains of forgotten cultures may be hidden. One of the most intriguing cases is that of Doggerland, a territory that connected Great Britain with continental Europe during the last glaciation. About 8,000 years ago, the rising sea level completely submerged it. Today, fishermen and marine archaeologists have found stone tools, remains of hunted animals, and evidence of human settlements under the seabed. Doggerland reminds us that glaciations not only covered lands, they also transformed coasts and erased entire maps. And if this is true for such a recent period, what could have happened in much older glaciations when not only the coasts changed, but the complete geography of the planet? During the glaciations of the Neoproterozoic, or even the early Pleistocene, entire areas could have been devastated, leaving scarce traces for us. In recent years, underwater archaeology has provided clues that fuel speculation. Off the coasts of India, in the Gulf of Khambhat, sonar explorations have detected what appear to be rectilinear structures and geometric patterns at depths of more than 30 meters. Some scholars maintain that they could be natural formations, but others suggest that they could be the remains of a city submerged more than 9,000 years ago, when the sea began to reclaim ancient lands. Further north, in Japan, the Yonaguni structure, submerged near Okinawa, has caused similar debates. Its stepped platforms, right angles, and massive shapes look artificial, but there is no consensus. What we do know is that if there were ever coastal cultures before the end of the last glaciation, the sea has done an impeccable job of hiding them. Glaciations could also have been catalysts for massive migrations. The advance of the ice forced human groups to move towards more temperate zones, carrying with them knowledge and technologies that merged with those of other peoples. This could explain surprising similarities between cultures separated by thousands of kilometers. although it could also be simple cultural convergence. If we allow ourselves to speculate, and this is where imagination mixes with science, it is possible to think of prehistoric societies that, adapted to temperate climates, flourished during interglacial periods and disappeared when the ice advanced again. Some could have reached a notable level of organization and construction, but their works made of stone, wood, and mud did not resist the onslaught of thousands of years under the glacier. In this sense, the ice is both a destroyer and a protector. In some places, it has preserved objects extraordinarily. The body of Ötzi, the Iceman found in the Alps, remained intact for more than 5,000 years, with his clothing and tools almost complete. If a simple individual could be preserved like this, what other remains could be waiting in deeper layers of ice, in glaciers that have not yet revealed their secrets? The problem is that the thaw caused by current climate change could release some of those remains, but also destroy them quickly. Contact with air and modern microorganisms degrades materials that remained stable for millennia. What melts today could disappear forever before we have a chance to study it. Thus, the hypothesis of lost civilizations linked to ice ages remains in the realm of conjecture, but it is not a baseless fantasy. Geology tells us that glaciations have erased entire landscapes. Archaeology shows us that entire regions submerged today were inhabited. And anthropology reminds us that myths, although adorned with time, often contain a core of truth. If one day we find irrefutable proof of an advanced culture, predating the dates accepted by official history, it is likely to be in two places, under the sea or under the ice. And both scenarios are difficult to explore, although not impossible. What is certain is that every time the ice advances and retreats, it leaves a clean canvas for life, and perhaps civilization, to reinvent itself. We are just the last of those reinventions. There is no guarantee that we will be the last at all. Imagine a world dominated by white and silence. The wind sweeps across frozen plains, dragging snow crystals as if they were tiny needles. Between ice-covered mountains and partially frozen seas, creatures move that seem taken from a mythological bestiary: hairy behemoths, giant birds, felines with impossible fangs. These were the true sovereigns of the Ice Ages. The most iconic image is, without a doubt, that of the woolly mammoth, Mammothus primigenius. These relatives of modern elephants were perfectly adapted to the extreme cold. Their fur was so dense that beneath it they kept a layer of fat up to 10 centimeters thick that protected them from the polar wind. Their ears were small, a key adaptation to avoid heat loss, and their trunk, strong and flexible, allowed them to remove snow to reach hidden grass and mosses. The curved and elongated tusks could reach more than 4 meters and were used both for defense and for clearing hard snow. Beside them roamed the woolly rhinoceros, Coelodonta antiquitatis, covered in a thick coat of brown hair and with a massive body designed to withstand blizzards. Their horns, longer and flatter than those of modern rhinoceroses, helped them scrape the frozen ground in search of food. But not all were giant herbivores. At the top of the food chain, undisputed kings of the ice, were the cave lions, Panthera leo spelaea, felines larger than any modern lion, without a mane, with bodies adapted to conserve heat and powerful paws for hunting in difficult terrain. These predators could take down large prey, including young mammoths. And perhaps the most emblematic of the glacial carnivores is the saber-toothed cat, Smilodon fatalis and Smilodon populator. With fangs that could exceed 20 centimeters and a robust body, it was a specialist in ambushes. It did not run long distances. It preferred to stalk and attack with explosive force, using its fangs to inflict lethal wounds. Beyond the large mammals, the ice ages were also home to impressive birds. The great auk, Pinguinus impennis, unable to fly, inhabited the cold waters of the North Atlantic. Its hydrodynamic body and dense plumage allowed it to swim long distances in search of fish, and its size, close to that of an emperor penguin, made it a coveted prey for prehistoric humans and natural predators. In the skies of the cold latitudes, birds of prey, such as the snowy owl, Bubo scandiacus, soared, perfectly camouflaged among the snow thanks to its white plumage. Its silent flight allowed it to hunt lemmings and other small creatures that moved under the snow. But perhaps the most fascinating thing about the fauna of the ice ages is its capacity for adaptation. Many of these species did not live solely in perpetual ice. They followed the seasons, migrated in search of food, or moved to warmer regions during the harshest winters. This dynamism allowed them to survive for thousands of years, until climate change and human expansion put an end to their reign. The end of the last ice age was for many of these animals the beginning of their disappearance. The thaw brought with it the loss of cold habitats and the expansion of forests where there were once frozen grasslands. Mammoths, for example, were confined to isolated islands, such as Wrangel Island in the Arctic, where a small group survived until just 4,000 years ago. Woolly rhinoceroses disappeared shortly before, and the great predators, deprived of abundant prey, followed the same fate. In some cases, the relationship between humans and glacial fauna was direct and lethal. Cave paintings in France and Spain show mammoths, bison, and woolly rhinoceroses in surprising detail, a sign that our ancestors not only saw them, but hunted them. Stone tools found next to bone remains with cut marks confirm that these animals were an essential part of the human diet. However, not all interaction was hunting. In certain contexts, humans may have followed these animals to take advantage of migration routes, learn about water sources, or locate safe passages between glaciers. In this sense, the megafauna of the ice ages was not only food, but also a guide. Beyond the giants, small animals also left their mark. The Arctic lemming, the Arctic fox, and the Arctic hare show how adaptation can take less spectacular, but equally effective forms. Furs that change color according to the season, padded paws for walking on snow, and compact bodies to retain heat. What these creatures tell us, large and small, is that life always finds ways to persist, even in the most extreme climates, and that when the balance is broken by natural changes or human influence, the impact can be irreversible. Today, fragments of that world still survive. The European bison, the reindeer, the grey wolf, and the brown bear are descendants of lineages that prospered in the ice ages. Their mere existence is a living link to a time when the planet was much colder and more hostile, but no less vibrant. And if you ever tour a natural history museum and find yourself in front of a mammoth skeleton or a saber-toothed cat skull, remember that they are not just remains of extinct animals. They are witnesses of a lost world, of a fragile balance that the ice and time can no longer return. Because in the end, these animals of the eternal snow teach us that survival is not always a matter of brute force. Sometimes it is a matter of adapting just fast enough before the ice advances or the sun warms up again. Just a sigh ago, in geological terms, the planet was trapped in the last great glaciation. It was such a recent period that our own ancestors lived through it and remembered it in their myths and legends. Science calls it the last glacial maximum, and it began about 115,000 years ago, reaching its most extreme point about 21,000 years ago, before definitively retreating towards the temperate climate in which we live today. If we could go back to that moment, we would see a very different planet. North America was covered by a layer of ice called the Laurentide ice sheet, a white monster that stretched from the Arctic to what is today New York. In Europe, the Fennoscandian ice sheet covered Scandinavia, much of the British Isles, and extended towards Russia. Greenland and Antarctica were even more extensive than now, and mountain ranges on all continents housed glaciers that descended to valleys that are green and fertile today. The sea level was up to 120 meters below the current one. This left exposed vast coastal plains that today lie submerged beneath the ocean. For example, what is today the North Sea was then an immense grassland known as Doggerland, inhabited by herds of mammoths, woolly rhinoceroses, and human groups that hunted and gathered on its banks. The global climate was much colder and drier. Large frozen deserts covered areas that today have forests, and extensive regions of tundra stretched across Eurasia and North America. The winds were stronger, and the dust dragged from the arid lands traveled thousands of kilometers, depositing in layers visible even today in lake and glacial sediments. For the humans of that time, this world was not a postcard landscape. It was a constant challenge. Hunter-gatherers had to follow the movement of migratory animals, adapt to more extreme seasons, and build shelters that could withstand the cold. Some groups lived in caves, others in huts made with mammoth bones covered with skins. Survival depended not only on strength, but on cooperation and a deep knowledge of the Earth and its cycles. The extreme cold was not uniform across the planet. In regions near the equator, temperatures were milder, but the impact of the glaciation was felt equally. Rainfall patterns changed. Rivers modified their courses, and entire ecosystems reorganized. Even in the tropics, the mountain peaks were covered by glaciers, as happened in the Andes or on Mount Kilimanjaro. One of the most interesting factors of the last glacial maximum is how it shaped the human map. Low sea levels created land bridges that are submerged today. The most famous is the Beringia land bridge, which connected Siberia with Alaska. Through this corridor, human and animal groups crossed from Asia to America and vice versa. Beringia was not a simple, frozen pass. It was a vast region of cold grasslands, rich in fauna, that served as a temporary home for those who crossed it. But even in the midst of that icy world, the ice was never static. Glaciers advanced and retreated, breathing with the pulse of the climate. In some periods, glacial lakes formed so large that when their natural ice dams gave way, they caused catastrophic floods. One of the most impressive occurred in North America, when the glacial Lake Missoula suddenly emptied, releasing a torrent that swept away hundreds of kilometers and carved landscapes like the channeled scablands in the current state of Washington. In Eurasia, similar events may have changed migration routes and altered entire ecosystems. The retreat of the glaciers not only released water, but also created new valleys, rivers, and lakes that today are part of the geography we know. The end of the last glaciation was fast in geological terms, but not immediate for those who lived through it. The climate began to warm about 15,000 years ago, with dramatic ups and downs. One of them, the Younger Dryas, was a sudden return to cold that lasted about 1,200 years before the planet resumed its path toward warmer temperatures. This episode demonstrates that the climate can change abruptly, even when it seems to follow a stable trend. With the retreat of the ice, sea levels began to rise. Entire coasts disappeared under the waters, forcing human communities to move and adapt to new environments. The sea level rise was not uniform. In some regions, isostatic rebound, the lifting of the Earth after losing the weight of the ice, partially compensated for the rise. In others, the water advanced rapidly, reclaiming lands that had been home for generations. The megafauna that had reigned for millennia began to become extinct. Mammoths, woolly rhinoceroses, giant deer, and many others could not adapt to the new climate or the pressure of human hunting. Their disappearance changed the ecosystems forever, altering food chains and landscapes. In cultural terms, the end of the last glacial maximum coincided with profound transformations. In some regions, the abundance of resources allowed humans to settle for longer periods in the same place, experimenting with the cultivation of plants and the domestication of animals. This change laid the foundations for the agricultural revolution that would arrive a few millennia later. And yet, in the midst of all this change, the memory of the ice remained engraved in the collective memory. The legends of great floods, the stories of lost lands, and the myths of epochs of extreme cold are not simple inventions. They are echoes of a time when the world was divided between ice and free land. Today, by studying the last glacial maximum, we not only understand the past, we also see a mirror of the future. The climatic cycles that led that ice to advance and retreat still exist. And although human action has drastically altered the natural balance, the planet preserves, in its geological memory, the capacity to transform itself on scales that surpass us. The last great ice reminds us that the stability we enjoy now is actually a brief pause. The Earth's climate has never been static, and our civilization, however solid it may feel, is as vulnerable as those that saw the ice advance. When we think of the ice ages, we usually imagine vast continents covered by kilometers of ice, frozen seas, and an unrecognizable planet. But not all glaciations have been so extreme. Throughout more recent history, the Earth has experienced abrupt and persistent coolings that, without freezing the entire planet, left deep traces on human life, nature, and history. We know these episodes as little ice ages. One of the most studied occurred between the 14th and 19th centuries, a period in which global temperatures dropped enough to transform landscapes, alter harvests, and change the course of entire civilizations. It was not a constant cold, but a series of prolonged cold phases, separated by warmer intervals. And although its magnitude does not compare with that of the great glaciations, its impact was immediate and evident to those who lived through it. In Europe, winters became longer and more severe. Rivers like the Thames in England or the Seine in France froze so frequently that winter fairs were organized on them. Paintings by artists of the time show festive scenes on the ice, makeshift markets, games, and dances. But behind that picturesque image was a harsh reality. Crops failed more often, famines multiplied, and epidemics found fertile ground. In other parts of the world, the effects were equally significant. In China, the Yellow River and the Grand Canal froze, interrupting vital trade routes. In Japan, colder winters contributed to poor harvests and social unrest. In the southern hemisphere, glaciers in the Andes visibly advanced, invading valleys and covering farmlands. The causes of this little ice age have been a subject of debate. The most accepted combination includes a decrease in solar activity, known as the Maunder minimum, an increase in volcanic activity that filled the atmosphere with reflective particles, and changes in ocean currents. These factors, acting simultaneously, reduced the amount of heat that reached and was retained on the Earth's surface. In North America, the prolonged cold affected indigenous populations, altering hunting and fishing patterns. In Greenland, the Viking colonies that had been established centuries earlier began to disappear. Archaeological records show a retreat of agricultural activity, the loss of livestock, and an increase in dependence on marine hunting, until these communities were finally abandoned. The Little Ice Age also left a deep mark on culture and art. Many works of the time, from chronicles to paintings, reflect unusually cold and snowy landscapes. In music, composers like Vivaldi and his famous Winter from the Four Seasons capture the intensity of the climate and the relationship people had with it. But the little ice ages are not limited to this period. There were others in earlier history. Between the 6th and 7th centuries, a cold episode affected much of the northern hemisphere. Recent research suggests that it may have been due to a series of massive volcanic eruptions that released ash and sulfur dioxide into the atmosphere, blocking sunlight. Chronicles of the time speak of years without summer, turbid skies, and failed harvests. This cooling coincided with political and social crises in several empires, from the Byzantine to the Chinese Empire. Even further back, around the year 1000 before our era, indirect climate records suggest another prolonged cooling that may have influenced the collapse of late Bronze Age societies. Droughts, cold, and food shortages would have created a perfect scenario for massive migrations and conflicts. The most interesting thing about these little ice ages is how they reveal the close connection between climate and human history. Relatively modest changes in average temperature, barely 1 or 2 degrees less than usual, can alter the balance of ecosystems, displace agricultural frontiers, and trigger economic and political crises. The resilience of a society, its capacity to adapt or collapse, was put to the test every time the climate decided to change the script. And like the great glaciations, these recent coolings remind us that the Earth's climate is dynamic, that there is no established long-term normality. Temperate periods, like the one we live in now, are exceptions in a history marked by constant changes. Today, when we look back and study the little ice ages, we find in them not only a lesson about the past, but also a mirror for the present. They show us how entire societies adapted or failed to adapt to abrupt changes in the climate, and how, even in times of adversity, innovations, new forms of organization, and cultural expressions emerged. In a sense, the little ice ages invite us to reflect on human fragility and resistance, on how, in the midst of cold and scarcity, life continues to seek ways to continue, and on how every climatic change, however small it may seem in the graphs, can be enormous in the lives of those who experience it. On the scale of human history, we live in a privileged moment. The climate is, in comparison with most of the geological past, benign and stable. Seasons follow one another with predictable regularity. Glaciers are confined to the poles and high mountains, and vast regions of the planet are fertile and habitable. But that calm is not eternal. If we heed the natural patterns of the terrestrial climate, we are living in a pause, an interlude between glaciations, and every pause, by definition, ends. Geological records and ice core analyses show a pattern. Throughout the last 2.5 million years, the Earth has alternated between glacial and interglacial periods, with an approximate cycle of 100,000 years. In that cycle, the cold phases with large layers of ice covering continents last much longer than the warm phases. Periods like the current one are brief exceptions before the ice advances again. If we follow the logic of this pattern, the Earth's climate should be heading toward another ice age in the coming millennia. The question is not so much whether it will happen, but when and under what conditions. The natural causes of these oscillations are well studied. Changes in Earth's orbit and the inclination of its axis, the so-called Milankovitch cycles, alter the amount and distribution of sunlight that reaches the surface. Added to this are factors such as volcanic activity, atmospheric composition, and the position of the continents. Under natural conditions, a gradual decrease in solar radiation at high latitudes could initiate the accumulation of snow and ice, which in turn would increase the planetary albedo and reinforce the cooling. Once the cycle begins, the advance of the ice would become relentless. In a few tens of thousands of years, much of the northern hemisphere could be covered by layers of ice, several kilometers thick. But today, we live on a planet where a new factor alters that pattern: us. The current concentration of carbon dioxide in the atmosphere is the highest in the last 800,000 years. Some studies suggest that this increase could delay the onset of the next glaciation, keeping the planet in a prolonged interglacial state. However, not everyone agrees with this diagnosis. The climate is a complex system, and although we have altered its parameters, we do not control all the elements of the equation. This opens up an uncertain scenario. It is possible that, despite the current warming, the planet may experience abrupt coolings in the future due to natural factors or even unexpected interactions between our own emissions and the climate system. Changes in ocean currents, for example, could redistribute heat unevenly, causing harsher winters in certain regions, even while the global average temperature increases. If a new glaciation were to begin, the effects would be drastic for our civilization. Coastal cities would be abandoned, not due to rising sea levels, but due to the formation of glaciers in their latitudes. Agriculture would shift towards areas closer to the equator, creating tensions over land and water. Mass migrations would be inevitable, and the world's political map would be radically transformed. Such a future would not necessarily be an exact repetition of the past. Technology would give us tools to resist and adapt. Advanced greenhouses, geothermal energy, transportation systems in extreme climates, but we would also have unprecedented challenges. Maintaining global communication and supply networks in a world fragmented by ice would not be easy. Beyond survival, there is something profoundly philosophical in contemplating a frozen future. It reminds us that no matter how much we dominate our technology and believe we control our environment, we remain part of a living planet, subject to rhythms that we cannot completely stop. We live in a time span that on a geological scale is like a warm breath between two long winters. In this context, looking back becomes an exercise in foresight. The great glaciations show us which regions of the planet are most vulnerable, where glaciers could form, and what migration patterns could be repeated. The records of past fauna, flora, and cultures teach us which adaptation strategies have worked before and which failed. And we cannot ignore that, if a new ice age were to arrive, it would not do so alone. The planet is not a laboratory where a single change occurs in isolation. Climatic variations intertwine with changes in biodiversity, the availability of resources, and social dynamics. A future glaciation could coincide with radical technological innovations or energy crises, with advances in biotechnology, or with geopolitical tensions. Some scientists have proposed bold ideas to avoid or at least mitigate the advance of a glaciation, from geoengineering to adjust the terrestrial albedo to the deliberate control of the atmospheric composition. But these proposals are fraught with uncertainty and possible side effects. Intervening on a planetary scale would be like playing with the gears of a mechanism that we barely understand. Ultimately, thinking about a frozen future is not an exercise in science fiction, but a way of remembering that the Earth's climate has always changed and always will change. The current conditions, which seem normal to us, are exceptional, and what we take for granted today, stable crops, predictable seasons, safe coasts, is the product of an equilibrium that in the long history of the planet has rarely lasted so long. Perhaps tens of thousands of years from now, humanity, or whatever has evolved from us, will look back and remember this temperate interlude as a golden age, a brief time when the ice did not dictate where we could live. Or perhaps it will be us who see the first signs of a gradual cooling, the first persistent snows in mid-latitudes, and understand that the next chapter is already beginning to be written. Whatever the case, history gives us a certainty. The ice will return. The question is whether we will be prepared to receive it. The ice has memory, a long, patient memory, that silently guards the history of the planet long before we arrived. In its layers, centuries of winds, storms and seasons are recorded. Dust particles from deserts that no longer exist are preserved. Chemical traces of volcanic eruptions that darkened ancient skies. Chemical signals of seas that rose and fell like deep breaths. The ice is a living archive, and when we look closely, what it returns to us is a story of constant change. Throughout this journey, we have crossed glaciations that covered entire continents, small coolings that altered empires, and moments when cold and fire clashed to shape impossible landscapes. We have seen how colossal animals dominated the eternal snow, and how the retreat of the ice opened the way for new opportunities, for life, and for civilization. And perhaps most importantly, we have understood that these transformations are not simple, isolated chapters. They are part of a cycle that has not ended. The ice ages, on all their scales, have been engines of change. They have destroyed, but they have also created. They have erased cultures, but they have sown the ground for others to flourish. They have reduced biodiversity in an instant, only to cause evolutionary explosions shortly after. The ice is both a destroyer and a creator, a guardian and an executioner. Looking at the past offers us perspective. It reminds us that the Earth is not a static stage where human history unfolds without jolts. It is a main actor with its own script and its own rhythm, which sometimes coincides with our interests and sometimes completely ignores them. And in that script, cold has been a recurring force, a character that appears again and again, changing in form, intensity, and consequences. But beyond the geological, there is something profoundly human in this story, because the ice ages did not just shape the planet, they also shaped what we are. The cold forced our ancestors to cooperate, to develop more sophisticated tools, to perfect the use of fire, to innovate in the storage and preparation of food. Every prolonged winter made us more ingenious and more resistant. Without those challenges, our history would be very different, and perhaps our species too. It is easy to think that we live outside that cycle, protected by our cities, our technology, and our knowledge, but the reality is that we remain vulnerable. An abrupt change in climate, whether towards cold or heat, would have immediate consequences for our way of life. And if history of the planet teaches us anything, it is that those changes, however improbable they may seem in an instant, always end up arriving. Therefore, understanding the ice ages is not just an exercise in scientific curiosity, it is a way of preparing ourselves. It forces us to think on broader scales, to step out of the immediacy of the present, and to recognize that we live in an exceptionally temperate and exceptionally fragile moment. Beyond the cold, what we really find in this exploration is a simple truth. Everything changes. Glaciers advance and retreat. Seas rise and fall. Species appear and disappear. Cultures are born and vanish. And in the midst of that constant flow, the only thing we can do is adapt, learn, and, above all, remember. Remember that we are not the owners of time, but its guests. That the climate we feel as normal today is just a page in an immense book. That just as there were civilizations that lived and prospered before the ice reclaimed them, there could also be others after us. And perhaps therein lies the most important lesson, that the cold, however relentless it may seem, is also a bridge. It unites past and future. It connects us with creatures that walked on the snow thousands of years before we wrote the first word, and with generations that perhaps one day we'll contemplate glaciers where there are cities now. In the end, what we have seen is that the ice is much more than a climatic phenomenon. It is a reminder that the Earth is alive, dynamic, unpredictable, and that our place in it is as transitory as the heat of a summer in the middle of a glacial cycle. If you have come this far, if you have felt the same mixture of awe and humility as I have in touring this history, then you are already part of this journey. Because at Dato Terra we do not just tell facts, we explore the deep connections between the planet, its history, and ourselves. And if this way of looking at the world resonates with you, I invite you to stay, to continue exploring together the mysteries that the Earth guards under its ice, in its oceans, in its deserts, and in the sky above us. Subscribe, not to receive definitive answers, but to continue asking ourselves the right questions, because beyond the cold, there is always more to discover.